In southern Egypt, on the east bank of the Nile near the modern city of Aswan, a massive unfinished stone lies in a granite quarry, still physically connected to the bedrock from which it was being carved. This object, widely known as the Unfinished Obelisk, represents one of the most striking and perplexing remnants of ancient Egyptian engineering. It is not a ruin in the conventional sense, nor is it a completed monument worn down by time. Instead, it is a project frozen at the moment of abandonment, an artifact that captures intention without completion. The obelisk is carved from pink granite and measures approximately 137 feet in length. Its scale is difficult to grasp without comparison. It is roughly equivalent to the height of a 12-story building, yet it lies horizontally within a quarry trench. Its estimated weight is approximately 1,200 tons, placing it far beyond the scale of any obelisk that ancient Egypt successfully erected. Even today, moving a single stone of that size would require extensive planning, modern machinery, and specialized engineering solutions. The significance of this object becomes clearer when placed alongside other known achievements of ancient stoneworking. The largest obelisks that were successfully quarried, transported, and erected in ancient Egypt typically fall within a range of 400 to 450 tons. The most prominent example, the Lateran Obelisk, stands as a testament to what ancient Egyptian engineers demonstrably achieved. Rising approximately 32 meters in height and weighing around 455 tons, it represents the upper boundary of confirmed capability. Beyond Egypt, other ancient cultures also attempted to work with extremely large stones. The stone of the pregnant woman located in Baalbek is often cited as one of the largest stones ever quarried. Weighing approximately 1,000 tons, it was successfully cut but never transported. Its unfinished state mirrors the situation in Aswan, reinforcing the idea that quarrying massive stones was sometimes possible even when transport was not. The unfinished obelisk, however, exceeds both of these examples. It was not only larger than any successfully erected Egyptian obelisk, but also heavier than stones that ancient engineers elsewhere failed to move. Yet archaeological evidence strongly suggests that the ancient Egyptians intended to complete it. The shaping of the stone is advanced, the trenching around it is extensive, and the effort invested in its production indicates a deliberate and sustained project rather than an experimental attempt. The prevailing explanation within Egyptology is relatively straightforward. The obelisk was abandoned after a structural flaw, a crack, appeared in the granite. This crack is still visible today, running across the body of the stone in a way that would have compromised its integrity. Since obelisks needed to withstand significant stress during transport and erection, any internal weakness would have made the finished monument unsuitable for use. On this basis, the project was halted. This interpretation is supported by the archaeological context surrounding the quarry. Artifacts found in the area link the activity to the reign of Hatshepsut, a ruler known for commissioning ambitious construction projects, including multiple obelisks. The dating is consistent with a period of high architectural activity and experimentation within the New Kingdom. However, while the crack explains why the project stopped, it does not address a deeper and more complex question: how the Egyptians intended to complete it in the first place. To understand the magnitude of that question, it is necessary to examine what obelisks represented in ancient Egyptian culture. These structures were not merely decorative or commemorative. They were deeply symbolic objects tied to religious beliefs, particularly the worship of the sun god Ra. The obelisk's tall, tapering form and its pyramid-shaped top, known as the pyramidion, were designed to interact with sunlight, symbolizing the sun's rays and reinforcing the divine authority of the pharaoh. Because of this symbolic role, obelisks were required to be monolithic. They had to be carved from a single piece of stone. This requirement was not a matter of aesthetic preference, but of theological necessity. A joint or seam would have disrupted the symbolic unity of the structure, undermining its meaning. This insistence on monolithic construction imposed severe constraints on the engineering process. Builders could not assemble obelisks from smaller, more manageable blocks. Instead, they had to identify a natural granite outcrop large enough to accommodate the entire monument. Once identified, the stone had to be carved directly from the bedrock using tools that were, by modern standards, relatively primitive. The most widely accepted method for shaping granite in ancient Egypt involves the use of dolerite hammerstones. Dolerite is a hard igneous rock capable of chipping away at granite through repeated impact. Archaeological evidence supports this method. Dolerite balls have been found in quarries, and the surfaces of partially worked stones display marks consistent with pounding. This interpretation was formalized in early modern studies by Reginald Engelbach, whose analysis of the Aswan quarries established a framework that is still referenced today. According to this model, workers would systematically pound trenches around the intended shape of the obelisk, gradually isolating it from the surrounding rock. Experimental archaeology has demonstrated that this technique is viable. Reconstructions documented in Secrets of Lost Empires showed that teams using replica tools could successfully quarry smaller stones. These experiments confirmed that, given sufficient time and labor, granite can be shaped using pounding methods. However, scale remains the central issue. The stones used in experimental reconstructions typically weigh tens of tons, not hundreds or thousands. The difference is not merely quantitative but qualitative. As the size of the object increases, the time required for quarrying grows dramatically, and the margin for error decreases. A single flaw, such as the crack seen in the Unfinished Obelisk, can invalidate years of work. Even if the quarrying process itself is accepted, major uncertainties remain regarding how the final separation from the bedrock would have been achieved. One commonly proposed method involves inserting dry wooden wedges into slots, cut along the base of the stone, and then soaking them with water. As the wood expands, it exerts pressure on the surrounding rock, potentially causing it to split along a controlled line. While this technique is documented in later historical periods, its use in this specific context is not definitively established. The underside of the Unfinished Obelisk does not clearly display the characteristic wedge slots that would be expected if this method had been applied. This absence raises questions about whether a different technique was intended or whether the process had not yet reached that stage when the project was abandoned. Assuming that separation could have been achieved, the next challenge would have been extraction from the quarry. The obelisk lies within a trench cut into solid granite, meaning that once detached, it would still need to be lifted or maneuvered out of a confined space. The geometry of the quarry complicates this process, as there is limited room to construct ramps or leverage systems capable of handling such weight. At this stage, explanations become increasingly speculative. Proposed solutions often involve combinations of earthen ramps, wooden sledges, lubricated surfaces, and coordinated human labor. While these methods are plausible at smaller scales, their effectiveness at the scale of the Unfinished Obelisk has not been demonstrated. The difficulty is not simply one of effort, but of physics. The forces required to move a 1,200-ton object are immense, and the materials available, wood, rope, and human muscle, have inherent limits. Friction, structural stress, and the risk of catastrophic failure all increase with size. This pattern continues when considering transport. The Nile served as the primary transportation route in ancient Egypt, and there is clear evidence that obelisks were moved on large barges. Reliefs from Deir el-Bahari depict such operations in detail, showing massive vessels carrying multiple obelisks. However, these depicted obelisks are significantly smaller than the Unfinished Obelisk. Scaling up the design of these barges to accommodate a 1,200-ton load introduces additional challenges, particularly in terms of structural integrity and buoyancy. No direct evidence has been found for vessels of this capacity, leaving a gap in the reconstruction of the process. The final stage, erection, presents perhaps the most complex problem of all. The widely accepted method involves raising the obelisk using a combination of ramps and a sand-filled pit. The base of the obelisk would be positioned over the pit, and as sand was gradually removed, the stone would tilt into an upright position. This method has been shown to work for smaller obelisks. However, As with other stages, scaling introduces new difficulties. The forces acting on the base during rotation increase significantly with mass, and controlling those forces becomes more challenging. The risk of uncontrolled movement or structural failure rises accordingly. Taken together, these challenges do not necessarily prove that the Egyptians lacked the capability to complete the unfinished obelisk. However, they do highlight gaps in current explanations. Each stage, quarrying, extraction, transport, and erection, can be described in general terms, but the details become less certain as the scale increases. The unresolved questions surrounding the unfinished obelisk become more apparent when each stage of the proposed process is examined not just in principle, but in terms of physical constraints. It is relatively easy to describe how something might have been done. It is considerably more difficult to demonstrate how it could have been done within the limits of known materials, tools, and human capability. The first stage, quarrying, is often presented as the least problematic, largely because physical evidence supports the use of dolerite hammerstones. Yet even here, scale introduces complications that are frequently understated. Removing granite through repeated impact is not a precise or rapid process. It requires sustained labor over long periods, and the deeper the trench becomes, the more difficult it is for workers to operate effectively within it. For a monument the size of the unfinished obelisk, the trench would need to extend along its entire length and depth, with consistent accuracy to preserve the intended shape. Any deviation could introduce structural weaknesses or require additional removal of material, further increasing labor demands. The presence of the crack suggests that internal flaws within the granite could remain undetected until late in the process, meaning that large investments of time and effort carried significant risk. The second stage, separating the obelisk from the bedrock, remains one of the least understood aspects of the operation. While the wooden wedge hypothesis is often cited, its effectiveness at this scale is uncertain. The force required to fracture a continuous granite interface beneath a 1,200-ton block is immense. Even if expansion techniques were used, controlling the direction and uniformity of the split would be critical. An uneven separation could result in stress concentrations capable of damaging the stone. Another possibility is that the Egyptians intended to undercut the obelisk gradually, removing material from beneath it in a controlled manner. However, this would require workers to operate in extremely confined conditions while maintaining structural stability. Supporting the weight of the stone during this process would present additional challenges, as any premature shift could cause the obelisk to fracture or collapse into the trench. Once separated, the issue of extraction becomes central. The quarry itself imposes geometric limitations. Unlike open terrain, where large ramps can be constructed freely, a quarry confines movement within rigid boundaries of rock. To remove the obelisk, the Egyptians would likely have needed to construct a ramp system within or adjacent to the quarry, gradually elevating the stone to ground level. This raises several interrelated questions. How steep could such a ramp be without making movement impossible? What materials would be used to construct it? And how would those materials withstand the pressure exerted by a 1,200-ton load? Earthen ramps are frequently proposed because they are simple and consistent with other known Egyptian construction techniques. However, the stability of an earthen ramp depends on compaction, slope, and reinforcement. Under extreme loads, the surface could deform, increasing friction and reducing efficiency. Reinforcement with wooden beams might mitigate this, but wood itself has structural limits, particularly under compressive stress. The mechanics of moving the obelisk along such a ramp present further difficulties. The standard model involves placing the stone on a wooden sledge and dragging it using ropes pulled by large groups of workers. Lubrication, possibly with water, could reduce friction, as depicted in tomb paintings showing workers pouring liquid in front of sledges. Even so, the force required to initiate movement, static friction, would be enormous. Estimates based on smaller-scale experiments suggest that hundreds or even thousands of workers might be required. Coordinating such a workforce within the confined space of a quarry introduces logistical constraints. There must be sufficient room for workers to pull, for supervisors to coordinate, and for the ramp itself to accommodate the movement of the stone. At this point, the problem transitions from purely mechanical to organizational. Ancient Egypt was capable of mobilizing large labor forces, as demonstrated by pyramid construction and temple building. However, those projects typically involved repetitive tasks distributed across wide areas. Moving a single object of extreme mass concentrates all effort into a narrow operational zone, increasing the complexity of coordination. If the obelisk could be extracted and brought to the surface, the next phase would involve transporting it to its intended destination, likely the temple complex at Karnak. This journey would primarily take place along the Nile, the central artery of ancient Egyptian logistics. Evidence for river transport is strong. Reliefs from Deir el-Bahari depict obelisks being carried on large barges, often accompanied by multiple support vessels. These scenes illustrate not only the size of the transport ships, but also the level of organization involved, including crews, steering mechanisms, and possibly towing systems. However, the obelisks shown in these depictions are considerably smaller than the unfinished obelisk. Scaling up barge design introduces significant engineering challenges. The hull must distribute weight evenly to prevent structural failure, while also maintaining buoyancy. The draft of the vessel, how deep it sits in the water, would increase with weight, potentially limiting navigation in certain parts of the river. The construction of such a vessel would require large quantities of timber, a resource that was relatively scarce in ancient Egypt and often imported. Joining the timbers in a way that could withstand the stresses of a 200-ton load would demand precise craftsmanship and robust fastening techniques. While Egyptian shipbuilders were highly skilled, direct evidence for vessels of this capacity has not been identified. Stability is another concern. A long, heavy stone resting on a barge creates a high center of gravity, particularly if it is elevated on supports. This could make the vessel susceptible to tilting or capsizing, especially in response to currents, wind, or uneven weight distribution. Managing these risks would require careful planning and possibly additional support structures. Assuming the obelisk reached its destination, the final challenge would be erection. The sandpit method is widely accepted for smaller obelisks and is supported by both textual and experimental evidence. The process relies on controlled rotation, with the base of the obelisk settling into position as sand is removed from beneath it. At larger scales, however, the dynamics of rotation change. The moment of force acting on the base increases with both mass and length. As the obelisk begins to tip, its center of gravity shifts, accelerating the motion. Controlling this acceleration becomes increasingly difficult, and any loss of control could result in the stone crashing into place with destructive force. Rope systems could, in theory, be used to regulate the motion. Yet ropes made from plant fibers have tensile limits. Exceeding those limits would result in failure, potentially at a critical moment. Similarly, wooden braces or supports would need to withstand compressive and shear forces that increase dramatically with weight. These considerations do not necessarily invalidate the possibility of erection, but they do indicate that simple scaling of known methods may not be sufficient. Additional techniques, refinements, or innovations may have been required, none of which are clearly documented in the archaeological record. It is within this context that alternative interpretations emerge. Some researchers argue that the conventional model, while broadly plausible, does not fully account for certain observed features of the quarry. Christopher Dunn, for example, has suggested that the precision of some surfaces and the geometry of certain cut features may indicate the use of methods beyond simple pounding. These claims are controversial and are generally not accepted within mainstream Egyptology. Critics argue that variations in tool marks can be explained by differences in technique, tool condition, or later modifications. Nevertheless, the discussion highlights an important point. The archaeological record is open to interpretation, and different frameworks can produce different conclusions. A more conservative perspective is that the Egyptians possessed a high level of practical knowledge that is not fully captured in surviving evidence. Techniques may have been transmitted through apprenticeship rather than written documentation, leaving gaps in the historical record. In this view, the absence of explicit descriptions does not necessarily imply the absence of capability. Historical comparisons provide additional context. Large-scale stone movements in later periods are among the best documented engineering operations in history. The relocation of obelisks in Renaissance Europe, particularly under Pope Sixtus V, required complex systems of pulleys, scaffolding, and coordinated labor. These operations were meticulously recorded, offering insight into the challenges involved. Even with access to iron tools, advanced mathematics, and improved materials, these projects were difficult and risky. The stones involved were significantly smaller than the unfinished obelisk, yet the margin for error remained narrow. Failures could result in damage to the monument, injury to workers, or both. Similarly, the transport of Cleopatra's Needle during the modern era required industrial technology, including steam power and specially designed transport systems. Despite these advantages, the operations were complex and, at times, nearly disastrous. These comparisons do not prove that the ancient Egyptians could not have moved the unfinished obelisk. However, they emphasize the scale of the challenge. When later societies with more advanced tools encountered similar tasks, they required significant resources and planning to succeed. This raises a fundamental question. Were the ancient Egyptians attempting something that exceeded their practical capabilities, or did they possess methods that have not been fully reconstructed? One possibility is that the project represented an ambitious extension of existing techniques. The Egyptians may have believed that methods used for smaller obelisks could be scaled up, only to encounter unforeseen limitations. In this scenario, the crack in the stone may have halted a project that would have faced additional difficulties later. Another possibility is that the Egyptians had developed specialized techniques for large-scale operations that are not well documented. These could include variations in ramp design, more efficient use of lubrication, or innovative approaches to load distribution. Without direct evidence, such possibilities remain speculative but cannot be entirely dismissed. A third perspective is that modern interpretations may underestimate the cumulative effect of labor, organization, and experience. Ancient Egyptian society was highly structured, with the ability to mobilize and sustain large workforces over extended periods. Incremental progress, achieved through persistence and coordination, may have allowed them to overcome challenges that appear insurmountable when considered in isolation. The unfinished obelisk does not resolve these possibilities. Instead, it serves as a focal point for examining them. It highlights the intersection between intention and capability, between what was planned and what was achieved. What remains clear is that the obelisk represents a boundary condition in ancient engineering, a point at which known methods, available materials, and practical constraints converge in ways that are not yet fully understood. The discussion surrounding the unfinished obelisk often becomes polarized between two extremes. On one side is the assumption that ancient Egyptians must have had a fully workable method simply because they began the project. On the other is the claim that the task was impossible with known Bronze Age technology. Neither position, on its own, fully reflects the evidence. To move closer to a realistic understanding, it is necessary to examine the problem in terms of basic physics, specifically force, friction, weight distribution, and rotational dynamics. These principles do not depend on historical interpretation. They apply universally, regardless of time period or level of technology. The first critical factor is mass. At an estimated 1,200 tons, the unfinished obelisk represents an enormous concentration of weight in a single object. Mass directly influences inertia, which is the resistance of an object to changes in motion. In simple terms, the heavier an object is, the more force is required to start moving it, stop it, or change its direction. When the obelisk is at rest, the primary obstacle to movement is static friction, the force that resists the initiation of motion between two surfaces in contact. For a stone resting on a sledge, This force depends on both the weight of the stone and the properties of the materials involved, such as wood on stone or wood on compacted earth. Experimental evidence from smaller-scale reconstructions suggests that lubrication, particularly water, can significantly reduce friction. Ancient Egyptian tomb paintings show workers pouring liquid in front of sledges, indicating that this technique was known and used. However, even with reduced friction, the force required to move a 200-ton object remains extremely high. To put this into perspective, the number of workers required to generate sufficient pulling force would likely be in the thousands, depending on conditions. Each individual contributes only a limited amount of force, and coordination becomes critical. If workers pull out of sync, energy is lost and movement becomes less efficient. Maintaining consistent, synchronized effort over long periods is a logistical challenge in itself. Another important factor is ground pressure. The weight of the obelisk would be distributed through the sledge onto the surface beneath it. If that surface is not sufficiently compacted or reinforced, it could deform under the load. This deformation increases resistance and may even cause the sledge to become stuck. Reinforcing the ground with wooden beams or prepared pathways could mitigate this. But such measures require additional materials and planning. As the obelisk moves up a ramp, gravity introduces an additional opposing force. The steeper the ramp, the greater the component of gravitational force acting against the direction of motion. This creates a trade-off. A shallow ramp reduces the required pulling force but increases the distance over which the object must be moved. A steeper ramp shortens the distance but may make movement physically impossible. This trade-off becomes especially significant in the confined environment of a quarry. Space limitations restrict how gradually a ramp can be constructed, potentially forcing steeper inclines and increasing the difficulty of extraction. Once the obelisk is in motion, kinetic friction replaces static friction, generally making movement slightly easier to maintain than to initiate. However, maintaining motion requires continuous input of energy. Any interruption, such as uneven terrain, loss of coordination, or failure of equipment, can cause the object to stop, requiring the entire process to begin again. Transport by water introduces a different set of physical considerations. Buoyancy becomes the dominant factor, governed by the principle that an object will float if it displaces a volume of water equal to its weight. In theory, a sufficiently large barge could support a 200-ton load. The challenge lies in constructing a vessel capable of maintaining structural integrity under that load. The weight of the obelisk would need to be distributed evenly across the hull to prevent localized stress points. If the load is concentrated in one area, the hull could bend or fracture. Achieving even distribution requires careful placement and support structures, such as cradles or beams. Stability is also critical. A long, heavy object raises the center of gravity of the vessel, making it more susceptible to tipping. External factors such as wind, water currents, and shifting weight can amplify this instability. Managing these variables would require both careful design and skilled operation. The final stage, raising the obelisk into a vertical position, introduces the concept of torque, or rotational force. When the obelisk is tilted, its weight creates a turning force around its base. As the angle increases, this force changes, affecting how quickly the obelisk rotates. In the sandpit method, the goal is to control this rotation by gradually removing support beneath the base. For smaller obelisks, this allows for a relatively smooth transition from horizontal to vertical. However, as mass increases, the forces involved grow disproportionately. At a certain point, the weight of the obelisk can cause it to accelerate faster than it can be controlled. This creates a risk of sudden, uncontrolled movement. If the obelisk were to fall into place too quickly, the impact could damage both the stone and its foundation. Rope systems could be used to counteract this motion, providing tension that slows the rotation. However, ropes have tensile limits. Exceeding these limits would result in failure, potentially at a critical moment. Similarly, any supporting structures would need to withstand increasing loads as the obelisk approaches vertical alignment, Understanding these physical constraints helps clarify what is and is not known about the unfinished obelisk. It also helps address several common misconceptions. One widespread misconception is that the existence of the obelisk proves that the Egyptians had a complete and reliable method for handling objects of this size. In reality, the obelisk proves only that they began the process. It does not demonstrate that they had solved every stage of the problem. Another misconception is that the absence of a fully documented method implies the use of unknown or advanced technology. While it is true that not all ancient techniques are fully understood, there is no direct evidence supporting the use of machinery beyond what is consistent with Bronze Age capabilities. Proposals involving highly advanced or anachronistic technology are not supported by the archaeological record. At the same time, it would be equally misleading to assume that current explanations are complete. The archaeological record is inherently incomplete, and many aspects of ancient practice were never recorded in durable form. Knowledge may have been transmitted orally or through apprenticeship, leaving little trace for modern researchers. A more balanced interpretation recognizes that ancient Egyptian engineers operated within a framework of practical experience, experimentation, and incremental improvement. They successfully completed numerous large-scale projects, demonstrating a high level of skill and organization. At the same time, they may have encountered limits that were not immediately apparent at smaller scales. The unfinished obelisk can be seen as evidence of this process. It represents an attempt to extend existing techniques beyond previously achieved limits. Whether that attempt would have succeeded remains unknown. It is also important to consider the role of risk in large-scale projects. Even in modern engineering, ambitious undertakings involve uncertainty. Designs are tested, adjusted, and sometimes abandoned when unforeseen problems arise. The presence of the crack in the obelisk suggests that material risk was a significant factor. Granite, while strong, is not uniform. Internal fractures can compromise structural integrity, and detecting these flaws in advance is difficult without modern tools. In this context, the abandonment of the obelisk may reflect a rational decision rather than a failure. Continuing the project with a compromised stone would have risked wasting additional time and resources. Redirecting effort toward a new stone may have been more efficient. The broader question, how the Egyptians intended to move and erect the obelisk, remains open not because it is unknowable, but because it sits at the intersection of multiple uncertainties. Each stage of the process involves variables that are difficult to reconstruct with precision: material properties, workforce size, environmental conditions, and specific techniques. What can be said with confidence is that the problem is real. The obelisk exists, its dimensions can be measured, and the physical constraints can be calculated. These constraints do not make the task impossible, but they do define the boundaries within which any plausible explanation must operate. The unfinished obelisk, therefore, serves as a test case. Any proposed method must account for its full scale, not just simplified or reduced versions of the problem. It must explain not only how the stone could be shaped, but how it could be separated, moved, transported, and raised using the resources available at the time. Until such a method is demonstrated, either through experimental archaeology, at comparable scale, or through new archaeological evidence, the question remains open. This does not diminish the achievements of ancient Egyptian engineering. On the contrary, it highlights the extent of those achievements by drawing attention to the limits at which they operated. The unfinished obelisk is not simply an anomaly, it is a boundary marker, indicating the edge of what is currently understood. The granite outcrops near Aswan were not chosen at random. This region contains some of the finest granite available in Egypt, dense and durable, suitable for monuments intended to last indefinitely. Quarry workers would have identified a section of bedrock large enough to accommodate the full dimensions of the intended obelisk. This alone required experience. Choosing the wrong section, one with hidden fractures, would result in failure, as appears to have happened here. Once selected, the stone would be outlined directly on the rock surface. Workers likely marked the intended shape before beginning excavation, ensuring that the dimensions aligned with the requirements of the commission, possibly ordered under Hatshepsut. The second stage is isolation. Using dolerite hammerstones, workers would carve trenches along the sides of the obelisk, gradually separating it from the surrounding bedrock. This process was methodical and repetitive. Teams of laborers would pound the granite surface, breaking it down incrementally. Over time, these trenches deepened, defining the shape of the monolith. The trenching visible around the unfinished obelisk confirms that this stage was well underway. The sides are largely defined, indicating that the Egyptians had already committed significant time and labor to the project. At this point, the obelisk is still attached along its underside. The third stage, separation, is where uncertainty increases. Plausible reconstruction is that the Egyptians intended to leave small contact points beneath the obelisk while completing the shaping process above. This would allow the stone to remain stable during carving. Only after the upper surfaces were finished would they attempt final separation. If wooden wedges were part of the plan, they would likely have been used at this stage. Workers could have inserted wedges into prepared slots along the base, then introduced water to expand the wood and apply pressure. The goal would be a controlled fracture along a predefined plane. Alternatively, they may have used a combination of pounding and levering, gradually weakening the remaining stone beneath until the obelisk could be freed. Either approach would require careful coordination to avoid uneven stress that could crack the stone, precisely the kind of flaw that ultimately ended the project. Assuming successful separation, the obelisk would then lie fully detached within the quarry trench. This leads to the fourth stage, extraction. The most plausible method involves the construction of an earthen ramp. Evidence from other Egyptian construction sites suggests that ramps were a standard solution for moving heavy objects vertically or across uneven terrain. In this scenario, workers would build a ramp extending from the floor of the quarry to ground level. The slope would need to be shallow enough to allow movement, yet steep enough to fit within the available space. This balance is critical. The obelisk would be placed on a wooden sledge, possibly custom-built to distribute its weight evenly. The base of the sledge might be reinforced with beams or runners to reduce pressure on the ground and prevent sinking. Lubrication would likely play a key role. Water poured in front of the sledge could reduce friction between the wood and the ramp surface, a technique supported by visual evidence in tomb paintings. Teams of workers would then pull the sledge using ropes, likely made from plant fibers such as flax or papyrus. Coordination would be essential. Workers would need to pull in unison, guided by supervisors to maintain consistent force and direction. Given the scale of the obelisk, the workforce involved could be substantial. However, it is unlikely that all workers would operate simultaneously in the confined quarry space. Instead, the process may have been staged, with different groups rotating in and out or working in coordinated sequences. As the obelisk moves upward, additional measures might be required to stabilize it. Side supports or guide rails could help prevent lateral movement, reducing the risk of tipping or shifting. Once the obelisk reaches ground level, the next phase begins: overland transport to the river. Although the distance from the quarry to the Nile is relatively short, the challenge remains significant. The terrain would need to be prepared, possibly with a constructed roadway or track system. Wooden planks, compacted earth, or even stone pathways could be used to create a stable surface. The same sledge system would likely be used for this phase, again relying on lubrication and coordinated pulling. The goal would be to bring the obelisk to a loading area at the riverbank. This leads to one of the most critical transitions in the entire process: transferring the obelisk onto a transport vessel. The Egyptians are known to have used barges for moving large stones. Reliefs from Deir el-Bahari depict obelisks being loaded and transported along the Nile. These images show large vessels supported by multiple boats, suggesting that load distribution and stability were key considerations. For the unfinished obelisk, the scale would require an even more substantial system. One plausible approach involves constructing a barge in a partially submerged position, allowing the obelisk to be slid or lowered onto it. Alternatively, the riverbank could be shaped to create a gradual incline, enabling the sledge to move directly onto the vessel. Once loaded, the obelisk would need to be secured. Wooden supports or cradles could prevent movement during transport, distributing the load across the hull. The journey along the Nile to Karnak would depend on seasonal conditions. High water levels during the annual flood would increase navigability and reduce the risk of grounding. Crews would need to manage currents, wind, and steering, possibly using multiple support boats. Upon arrival, the final stage begins: erection. The most widely accepted method involves the use of a sand-filled pit. A ramp would be constructed leading up to the installation site, allowing the obelisk to be positioned horizontally above the pit. The base of the obelisk would be aligned with a prepared socket, carefully shaped to receive it. The rest of the stone would extend over the pit, supported by the ramp and surrounding structures. Workers would then begin removing sand from the pit in a controlled manner. As the sand level drops, the base of the obelisk descends, and the structure begins to rotate upward. This is the most delicate phase of the entire operation. The rate of sand removal must be carefully controlled to manage the speed of rotation. Too fast, and the obelisk could accelerate uncontrollably. Too slow, and the process could stall, placing uneven stress on the structure. Ropes attached to the upper sections of the obelisk could provide additional control, allowing workers to counterbalance the motion and guide the alignment. As the obelisk approaches vertical, the forces on its base increase. The socket must be precisely prepared to absorb this load and stabilize the structure. Once upright, final adjustments would ensure alignment and stability. The ramp and support structures would then be removed, leaving the obelisk standing as a permanent monument. This reconstruction does not eliminate uncertainty. At every stage, there are assumptions about materials, workforce size, environmental conditions, and technical details that are not fully documented. However, it provides a coherent sequence that aligns with known Egyptian practices while acknowledging the challenges introduced by scale. It suggests that the Egyptians were not attempting the impossible, but rather extending established methods to their limits. Whether those methods would have succeeded at this scale remains unknown. The crack in the unfinished obelisk ended the experiment before it could reach its most difficult stages. What remains is not proof of success or failure, but evidence of intent, an engineering plan interrupted. The unfinished obelisk remains exactly where it was left, cut into the granite bedrock near Aswan, incomplete, immovable, and unresolved. It is not hidden. It is not theoretical. It is a measurable physical object, and because of that, it does something rare in the study of ancient history. It forces a confrontation between assumption and evidence. At first glance, the explanation appears simple. A crack formed in the stone. The project was abandoned. Workers moved on. This is consistent with practical decision-making. It fits the archaeological context. It aligns with what is visible, but that explanation only answers why the project stopped. It does not answer how it was supposed to succeed. When all 5 stages are considered, quarrying, separation, extraction, transport, and erection, a pattern emerges. Each stage, taken individually, can be explained in general terms using known ancient Egyptian techniques. There is evidence for pounding granite with dolerite, for dragging stones on sledges, for transporting obelisks along the Nile, and for raising them using ramps and sand-filled pits. None of these are hypothetical. All of them are grounded in archaeology. The difficulty arises when those stages are combined and scaled. A method that works at 300 or 400 tons does not automatically work at 200 tons. Forces increase. Materials reach their limits. Margins for error shrink. Small inefficiencies become critical failures. This is where the unfinished obelisk becomes more than just an abandoned project. It becomes a boundary. A boundary between what is clearly demonstrated and what is only inferred. So what can actually be said with confidence? First, the ancient Egyptians had the capability to quarry, transport, and erect large monolithic stones. This is not in question. The existence of completed obelisks, including the Lateran Obelisk, confirms this beyond doubt. Second, they had a well-developed system of labor organization, logistics, and planning. Projects of this scale required coordination, resource management, and sustained effort over long periods. The Egyptians repeatedly demonstrated these capabilities. Third, the unfinished obelisk was not an isolated curiosity. It fits within a broader pattern of ambitious construction during periods such as the reign of Hatshepsut, when monumental architecture was closely tied to political authority and religious expression. But beyond these points, certainty begins to fade. There is no surviving document that describes, step by step, how a 200-ton obelisk was to be moved from quarry to temple. There is no completed example at that scale that can be studied directly. There is no experimental reconstruction that demonstrates the full process under comparable conditions. What exists instead are models, interpretations, built from partial evidence. Some of these models are conservative, extending known techniques and assuming that scale, while difficult, was manageable. Others are more speculative, suggesting that unknown methods or overlooked techniques may have been involved. Between these positions lies a gap, and it is within that gap that the unfinished obelisk continues to exist, not as proof of a lost technology, and not as evidence of failure, but as an open question. This distinction matters. It is easy to move too far in either direction, to assume that ancient engineers must have had capabilities far beyond what is currently understood, or to assume that they simply made a mistake and overreached. Neither conclusion is supported by complete evidence. Ancient Egyptian engineers were neither mysterious super-technologists nor careless experimenters. They were skilled practitioners working within the constraints of their materials, tools, and knowledge. They achieved remarkable results, but they also operated within limits that may only become visible at extreme scales. The unfinished obelisk may represent one of those limits, or it may represent a problem that had a solution, one that has not survived in the archaeological record. This uncertainty is not a weakness in the study of history. It is a reflection of how knowledge works. Evidence is incomplete. Interpretations evolve. Questions remain. And sometimes, the most important artifacts are not the ones that were finished, but the ones that were left behind, because they show the process, they show the ambition, and they show the point at which intention meets reality. The unfinished obelisk does not tell us exactly what the ancient Egyptians could or could not do. What it does is define the edge of what we currently understand about their capabilities. It forces modern observers, engineers, archaeologists, historians, to ask not just what happened, but how it could have happened. And until that question is answered with a method that accounts for the full scale of the problem, demonstrated, not just proposed, the discussion remains open. The stone is still there. The measurements are still the same. The problem has not changed. Only our attempts to explain it have. And for now, the most accurate conclusion is also the simplest. We know what they started. We know why they stopped. But we do not yet know how they intended to finish. That is the enduring significance of the unfinished obelisk of Aswan, not as a mystery waiting for a dramatic answer, but as a precise physical question carved into stone, still waiting for a complete explanation.